So here we are, exploratory factor analysis, or once again, we would discuss not only exploratory factor analysis, but we would discuss also the technique which is very close by the principle and also by results, and it is called principal components analysis. So we would cover these two techniques. First of all, only for you to know where we can find these techniques in JASP. So if I open JASP, it's again showing.
Excuse me, we don't see your screen. Oh no, okay, sorry.
Out of order. So currently you should see my screen. I hope so. If I go to JASP, we would find techniques for today's lecture in the dialog, which is called factor, and we would perform principal component analysis and exploratory factor analysis. And confirmatory factor analysis will be discussed in 3 weeks, I expect, in the lectures that will be devoted to structural equation models. So that's only first insight into JASP options, and once again, usually software packages mix principal component analysis and exploratory factor analysis into one technique, which is usually in these packages called factor analysis. For example, in SPSS, you can find this option. So there is only one procedure called factor analysis combining these two procedures in one option. So that's all for this first insight. And before we start, it would be good to give some brief insight. So it means describe why we are using exploratory factor analysis. We would use pictures as well as some equations once again. And we will give also some real examples of usage of exploratory factor analysis. And of course, the main goal of today's lecture would be to recognize how we can perform exploratory factor analysis in JASP. And we would discuss individual settings and outputs that are available in JASP. I would like to say that currently JASP is a very, very nice package for factor analysis. So we would have one of the best options how we can perform exploratory factor analysis and related component analysis through JASP. So first of all, we would start with a pre-description. What is exploratory factor analysis? Or we would be using quite often only the shortage EFA. So it means the first letters of exploratory factor and analysis. So the main goal of exploratory factor analysis is to explore data. That's quite easy to guess if it is exploratory. So maybe that I do not have any idea what is behind my data, and I am performing exploratory factor analysis to discover something which is behind my data. We call this phenomenon, which is maybe behind my data, as underlying structure, or sometimes we are discussing about factors. Factors means that these are variables that are not directly measured. So it means I'm not able to find these factors in my data matrix. There is no factor here. Only variables that are measured directly are present here. We call usually these variables as manifest variables. So manifest variables are these measured by my questionnaire or some testing instrument. So these are manifest variables. So columns which are in my data matrix are manifest, are observed or measured directly. And factors that are maybe behind my data, behind my manifest variables, are called factors. That's why we are discussing about factor analysis. And let's start with, I would like to say, the oldest example of usage of exploratory factor analysis, and this is the case included in Psychology of Intelligence. and this example is about intelligence itself. So I guess that everybody has some idea what is intelligence. And now let's briefly reproduce the history of intelligence discover, which was made at the beginning of 20th century. And the man who is behind this concept and behind the concept of the first usage of exploratory factor analysis is Charles Spearman. I guess you are familiar with this name. Do you know some Spearman invention in statistics? Do you know some formula which has the same name as Spearman?
Spearman correlations?
Yeah, and correlations for which variables are Spearman's? Cardinal, ordinal, or nominal?
For ordinal and cardinal.
Yeah, mainly for ordinal variables. Sometimes his coefficient, which is usually named as Spearman's coefficient, is sometimes called as Spearman's coefficient based on orders or ordinal Spearman's coefficient. So this is mainly for ordinal variables. Okay. So it means that the main goal of Spearman's statistical trials, let's call it like this, were to find relationships between variables. That was the first step for factor analysis. So first of all, Spearman, who was mainly interested in the psychology of intelligence, or who maybe invented this branch of study, tried to find whether there could be some relationship between individual results of tests for kids. If I remember well, there tests that Spearman's applied were tests of individual languages such as French, English, Latin. Also, there was a test for mathematics, and maybe there were more of these tests. And for all these tests, according to correlation coefficients, Spearman discovered that these results are somehow related. What's your expectation about this relationship? These were positive or negative relationships? What could be the relationship between individual tests for branches such as Latin, French, English, mathematics, etc. for kids? Positive or negative relationship you would expect for these tests? The better you are, for example, in Latin, the better you are in French, or opposite could be true?
I would say positive relationship.
Not only positive, but Spearman discovered that these relationships were quite strong. So it means that these correlation coefficients were quite big. So, and as Pearson computed these correlations, once again, it is more than 100 years ago, so computed by hand. He said, okay, maybe there is something behind this result, something behind these tests. And I would call it as small g, and the full name for this first concept of intelligence was, it is general intelligence, which is behind the results of these individual tests. And the logic, which is behind exploratory factor analysis itself, is the same. There is some hidden phenomenon behind my observed data. So for example, if I have here some data matrix with some variables, maybe there is something behind these data. For example, and we would start this example only by our sociological imagination tool, we would be performing exploratory factor analysis for a set of statements. So we wouldn't test anything, but we would use some questionnaire items. And here we have, for example, first 5 items that you can find in data file as A47A up to A47E. And I would rephrase these statements, and maybe you could try to tell me whether there could be some hidden dimension behind these statements and what could be maybe the meaning of this dimension. So the first statement is following. The government should redistribute incomes from those who are getting better to those who are getting worse. The owners of big companies are getting rich of the workers, and the second statement. Ordinary working people do get just a proportion of the national wealth. There is one justice for the rich and one for the poor. And the last one statement here in the first 5 statements says that the management will always try to get ahead of the employees if it takes a chance. These 5 statements should be answered by the scale of agreement, so from definitely agreement to definitely disagreement. And now my question is, without any computations, of course, we would perform exploratory factor analysis on these data. If you can see some hidden dimension behind these statements, if there could be something behind these data, if there could be some factor which is hidden behind my data. So some guesses, please.
Left and right-wing political orientation.
Okay, maybe some students are familiar with this topic and you expect that these 5 statements maybe measure left-right orientation. Yeah, you are definitely right. So we would, of course, then empirical prove that there is some hidden dimension behind these 5 statements. So this is simple logic of exploratory factor analysis by 2 examples. Intelligence by Spearman, and this left-right scale from political sociology. So this is a well-known 5 items set, which is usually performed in International Social Survey Program or just ISSP data. So we can go further. And maybe it would be good before we would continue our discussion and we would present pictures and equations to stop for a minute here and discuss about phenomena that cannot be measured directly. So, for example, intelligence cannot be measured directly. We do not have any special instrument by which we could directly measure intelligence. That's why psychologists invented many testing procedures that can help us indirectly to inquire intelligence of individual. Do you have some other examples ideally from social science of phenomena that cannot be measured directly, and that's why maybe exploratory factor analysis or related techniques could be employed if you would like to measure something?
I would say, for example, racism, that we cannot ask if you are a racist or not, but there should be some questions.
Maybe we could ask, but the answer would be totally biased. So you're definitely right, yeah. That would be a nice example. Some other example?
I would say, I'm sorry, I would say all the topics associated with social desirability.
Okay, and some example?
Yeah, like racism or drug abuse and these very sensitive topics.
Okay. Some other phenomena, not only social desirability would play a role, but I agree, this is a big phenomenon and it should be then applied some indirect measurements for these cases.
Maybe personality or psychopathology.
Okay, if you say personality, for example, well-known concept is so-called Big Five measurement tool. There are two versions, a broad one and narrow one. I guess that narrow one has approximately 10 or 11 items and big one 44 items. And there is expectation, or there is huge discussion in psychology whether there are 5 big traits from personality or lower or bigger number. Yeah, definitely. And do you also know maybe some sociological concepts that are also indirectly measured?
Maybe poverty?
Poverty could be indirectly measured, yeah. Some other phenomenons. For example, if I go back into the history of sociology and into historical founding fathers of sociology, and I would visit French for this time, and I would discuss about Emile Durkheim. What was the main idea of Durkheim? What was the main concept invented by Durkheim? How is it called? What was the biggest change or the biggest phenomenon for modern societies, according to Durkheim? It was anomie. And what is the meaning of this word?
Social anomie means that like people lost their ties in community as a result of industrial revolution, let's say very briefly.
Okay. Okay, so if I translate this phenomenon, so it is opposite of some order, opposite of some rules, as nomos mean rules in Greek language. And there were some trials. The well-known is invented by Leo Strula, American sociologist, to measure anomie at individual level. So there are also options how, for example, to measure anomie, and we could maybe name some other concepts in sociology that could be also measured indirectly. So thanks for this excursus and this play for indirectly measured concept in social sciences. And it is good to know at the beginning there are quite a lot of phenomena that are measured indirectly in social sciences. I would maybe add only for your information that maybe 2 disciplines use these indirect measurements most common, and this is mainly psychology, as we discussed. And also, you can find a lot of these indirect measurements in educational science. I would mention only some of these for you to know. So, for example, at the level of students and as well as at the level of teachers, there are phenomena that are called self-concept and also some self-evaluations. For students, there is something what is called academic futility, academic optimism for teachers, etc., etc. There are a lot of these concepts. So only for you to know that also educational science offer quite a lot of these indirectly measured concepts. And now we would go into some technical details. So we would be using pictures and equations to recognize what is behind the model of exploratory factor analysis from statistical point of view. So let's start with pictures, and then we will briefly discuss about equations. So first of all, very simple and maybe not realistic model, but for the first insight, it would help of exploratory factor analysis. So here we have a very simple picture, which is using squares or rectangles These shapes, and we would be using these shapes up to the end of this semester. So these shapes means that the variables inside this shape is the variable which is present in my data file. So it means it is real column in my data. It is manifest observed variable. So these are squares or rectangles. And there are also these circles or sometimes ellipses. And inside these shapes, we can find not observed or latent variables that are usually called factor. Once again, this is the reason why we call this technique as factor analysis. So factors are inside circles, and rectangles or squares are designed for observed variables. And as you can see on this picture, there are maybe two factors, two latent variables behind my data, which are consisted of 4 manifest variables. So originally I have 4 columns in my data matrix. And the main goal of exploratory factor analysis is to find these relationships, which are these green lines or these red lines. So it means these arrows starting from the factor and going to individual variables. So I can see that there is bad connection. Let me know if it is good.
Yes, now I can hear you.
So I would once again maybe go through the pictures. Sorry for that. So once again, yeah, I would repeat it, of course. So once again, so these shapes that are squares or rectangles include manifest variables. So it means variables that are present in my data matrix, that are real columns. These circles or ellipses include latent variables. So it means variables that are not in my data matrix, that are not observed. We call these variables as latent variables or factors. And the basic idea is that there is a link between factor and individual observed variables, and we try to evaluate the strength of the association of these links. So if I take these relationships, and if I take that this arrow is starting here and finishing here, so maybe you can help me to say what is dependent and independent variable in this case. Is I1 up to I4 independent or dependent? Is factor 1 and factor 2 independent or dependent? Please help me.
Factors are independent, they influence the dependent.
Yeah, as if we go by this arrow, which is one-headed arrow, so it goes from this point up to this point, so it seems this is independent variable and this is dependent variable. I would like only to warn you that through next lectures, we will slightly change these terms. So we would exchange the phrase independent and dependent by different phrases. But now for today's lecture, it is still enough. So what does it mean technically? It means that, for example, if there is some intelligence behind my tests, so the intelligence is something behind, and according to my intelligence, I can observe some results in individual tests. If I'm not discussing about intelligence, but for example about left-right scale, so according to my left-right orientation, which is something hidden in my head, I can observe some real answers in my data. That's the logic of this exploratory factor analysis by words. there is only one small edit part of models here, and these are small e's. Once again, they are in circles. So it means these variables also are not observed. And as far as you know, from previous discussion of regression models, you can expect that these small e's would be residuals. So it means unexplained variance for individual equations. So all these lines or relationships creates some regression equations, and for every equation there is some random part, some unexplained variance. We call these small e's usually as random errors, and they are not observed. That's why they are in these small circles, and they are closely related to dependent variable, as they mean technically what is unexplained by my equation and the rest is explained by factor 1 and factor 2 by these regression relationships. So this is technical explanation of factor analytic model by words and by picture. And if I go back here, we have a brief description by picture as well. So once again, observed variables, unobserved variables, and once again, these variables are also latent or unobserved variables. So we have 1, 2, 3, 4, 5, 6 unobserved variables, and we have 1, 2, 3, 4 observed variables here. Once again, this is very simple case and not a realistic case for real computations. So ideally, we would use factor analysis for more than 4 manifest variables. So that's only for you to remember, only as the picture could be very easy and very easily presented on this slide. That's why I decided to choose a very simple picture. And one more picture here, and only once again repetition that maybe there are only some regression equations behind these pictures. So I would start with the explanation by words on these pictures, and then on the next slide we would select all these equations and we would present these equations classically. So it means in the form dependent variable is equal to independence plus maybe some random error. So let's start with the first equation we can find here. So the first dependent variable is the first manifest or observed variable I1. And what would be the equation for I1? So I1 is influenced by factor 1 and factor 2, and also it is somehow influenced by some unobserved random error that could be present. And now it would be maybe nice if somebody could try to say me what could be the equation for this I1 variable. What would be classical regression equation for I1 according to this picture? Please try if you can. So I1 is equal to what? Nobody would try? Okay, so I would start this classical regression equation strategy. So I1 would be equal to maybe some intercept or constant at the beginning, then plus the impact of the first factor, so it means some regression coefficient multiplied by factor 1, plus the impact of the second factor, so it means maybe second regression coefficient multiplied by factor 2, plus random error, so it means this small e. only for factor analysis, that's only a technical detail, we would make two changes. For classical factor analysis, we would be performing, and also for structural equation modeling, we would be discussing in next lectures, it is possible to exclude from these equations intercepts or constants. So we wouldn't be discussing about intercept and or constants nearly up to the end of these lectures. So that's the first simplification. And the second change from classical regression settings, so I would be using discussions such as B1 would be the first regression coefficient, B2 would be the second one. So these regression coefficients, so it means the strengths of these associations, usually for factor analysis, are discussed as lambdas. So lambdas are these regression coefficients, and we call technically in factor analysis these lambdas as so-called factor weights. So lambdas are regression coefficients for factor analysis, and we call these as factor weights. Let's go to our model in a set of equations. So for I1, so it means this first item here, I would prepare the first equation. So I would take lambda and I would use two subscripts. 1 means it is for the first item, this is the first subscript, and for the first factor. So lambda 1 multiplied by factor 1, and lambda 1 multiplied by factor 2. Plus the first random error, and I would call this random error for the first observed item as E1. And the same or similar set of equations I can create for the rest. So it means for the second item, I would be using the second lambda 1 multiplied by factor 1 plus lambda 2 multiplied by factor 2 plus random error for the second item. So it means technically these e's should be changed into E1, E2, E3, E4. So for the third item, nearly the same set, only lambda 3 and 3 are present here. And for the last one, lambda 4 and lambda 4 And the main goal of exploratory factor analysis and the main goal for later interpretation would be that I would like to evaluate, to estimate these values of these lambdas. So it means that the values of these lambdas would help me to interpret my result. Let's imagine for simplicity that, for example, this lambda and this lambda is quite big value, and these lambdas are quite small value. It means close to 0. And let's imagine that if this would be true, it would mean that maybe these two items has some strong relationship to this factor 1. And if these two are not strongly related to this factor 1, so maybe that factor 1 is created by these two items, and we can use the meaning, common meaning of these two items for explanation what is the common factor behind. And let's imagine that also similar pattern is present for the second factor. So these two lambdas are close to 0, and these two lambdas are maybe quite big in their values. So maybe that this second factor is created mainly by these two items, and some common feature close or hidden in these two items is presented in factor 2. And for the interpretation of factor 2, I would use the meaning for these two items. What is common for these two items? That's my question. Once again, if I go back into our previous discussion, we have covered at the beginning. So I would be reading out the items and I would try to imagine what could be behind these items. That's the last step of exploratory factor analysis, which is called interpretation of factors. So now we are covering this topic theoretically. So this is technical step behind exploratory factor analysis by pictures as well as by equations. So technically, if I would rephrase this logic very simply, exploratory factor analysis is nothing more than set of regression equations in which individual observed variables are dependent and individual factors are independent. The only problem, or maybe this is slightly exaggerated, this is quite big problem maybe, the only problem is that I do not know how many factors are behind my data, and I do not know what are the values of these lambdas. So that's what must be solved technically, and that's what I need to perform in statistical package. As computation of exploratory factor analysis in hand is very, very time consuming. It would take hours to compute even such simple example as we have here. So here we have some preliminary questions of steps that should be performed in exploratory factor analysis. The first step is that I have a bigger set of manifest variables. For our case, so it means for today's lecture, we have here the set of items starting at A47A and finishing at A47K. So if I'm computing correctly, we have approximately 11 items here. So this is quite good for exploratory factor analysis to have more than 2 or 3 items. So we have here 11. So it seems that it would be possible to compute exploratory factor analysis. So this is the beginning. I have quite bigger set of manifest variables. So it means set of columns in my data. And my main goal is that I try to reduce this quite big set of original variables into small number of latent variables, once again called factors. So instead of originally, for example, 11 items, maybe I would be happy if I would get at the end of my analysis 1, 2, or 3 variables that will replace original data. That's why usually you can also discuss about factor analysis. Doesn't matter if we are discussing about exploratory or later we will cover also confirmatory version as the technique, which is a technique for dimension reduction. So it means instead of 4 variables, I have only 2 or maybe only 1. Instead of 11 variables, I would have only 1, 2, or 3 variables. So I am reducing in a big amount original number of variables into small amount of variables. So that's a technical reason or data analytical reason behind factor analysis techniques. So that's technicity which is behind, and we have quite a lot of questions once again. The first one question is whether there should be possibility somehow to replace original variables by factors that could be behind these variables. So maybe the first question is only, are these variables somehow related? Is there some relationship between these variables? So it means, is there some opportunity to replace original variables by factors? If these variables are not correlated at all, there is no space for factor analysis at all. So that's the first or preliminary question. If there are some relationships, there are more questions. So how many factors, how to extract these factors? So there are many, many techniques that can help us. And the last one question, but maybe the most difficult usually, is how we can interpret factors at the end. What is the meaning of the factors? We try this task previously. So we read these first 5 items, and we discovered that maybe behind these 5 items there could be left-right scale. So this is the logic we would apply at the end of our analysis, this interpretation step. So, and now I would start to compute some preliminary results. So before we enter into factor analysis, or its close relative principal component analysis, I would start with computation of correlation coefficients itself. In JASP, there is no option for correlations directly in factor analysis procedures. So we must perform correlation analysis by correlation procedures. It means go into regression and correlation. So we would start with correlations. But before we start, there is one technical information that must be added. So if we would like to perform factor analysis in JASP, currently at least for this version, which is 14.1, it is necessary to define all variables that we will use for computation as scale or cardinal variables. So as you can see here, all these A47A up to K are defined as ordinal, which is correct according to this data. But for computations of factor analysis in JASP, it is necessary to change into scale. So I would skip all these variables and define scales. I would only make small comment that if I'm changing, let's call it artificially, these settings for variables, I'm making small mistake and I will treat these variables as scale variables, but they are not so long scales originally. If I remember well, these scales include only 4 points. But unfortunately, JASP, and it is common for all statistical packages, usually do not offer special computation procedures for these shorter ordinal scales. So we would make a small mistake in these computations. And you should know that if you are using exploratory factor analysis for these shorter scales, the result is slightly worse than would be for some alternative algorithms. But once again, unfortunately in JASP and similar packages using exploratory factor analysis, there is no other option. So we should perform EFA also for this shorter scale with this knowledge about slight bias. It means our results will be slightly worse. One more comment or recommendation: if you would like to use special algorithms for shorter scales and you would like to use packages that are free, so there are, according to my opinion, 2 very good options. One option is to use some special packages in R or R project. So that's the first option. And the second option may be quite easy option for those of you who wouldn't like to prepare programs, is to use a software package which is called simply Factor. And it is a very nice freeware based on clicking. It means system of menus, which is also free, and it covers also procedures for short scales. Okay, so let's go back from this excursus about long and short scales, and we would go into regression and correlation from classical part in JASP. So here we are, and we would like to compute correlation coefficients for the set of all of these 11 variables. So I would take A for 7A up to K and move it into variables. And it is quite good not only to see classical table of correlations, as it would be quite big one and maybe not easy readable, but I would also recommend to also to go down. I must only wait for my JASP to compute the first result. And if you go down, you could find the output, which is called heatmap. It is something, I would say, between table and graphical output. So please ask also for this heatmap. And you would see output which is technically table, but I guess that in JASP it would be the output that seems like picture. And it is correlation matrix, so it means figures that are here. It means Pearson's correlations can be found in this heat map. We can check it 0.394 for the first two variables, 0.394 for the first two variables. And this output is quite nice, as it is graphically differentiated by the color. If I remember well, blue colors are for positive correlations and red colors for negative correlations. And if you can see dark colors, so it means there is bigger correlation here. And if you can see only colors which are nearly close to white, so these are very weak correlations. And if you take a look onto this picture, which is called heat map. Originally, it was invented in our project. So you can see that for my case, it seems that at least some variables are quite closely related. And these are first 5 items. So once again, if I go back to the discussion, we have discovered that maybe these 5 items are items about left-right scales. So it means that at least this dimension maybe will be discovered in exploratory factor analysis as some dimension which is describing left-right orientation. You can see that for the rest, so it means items starting from A47F up to A47K, there is no similar picture. So there is no darker area here. That should mean that there is also maybe some second dimension. Or at least we cannot find this dimension very easily here. Maybe there are some stronger relationships here. So it means maybe that 2 or 3 items are closely related, but there is no big set of items from A47F to A47K closely related here. So our expectation before we start to analyze this pattern by exploratory factor analysis is that we would find at least one dimension, and according to our previous interpretation, it would be maybe left-right scale. And maybe we would find very weak second dimension created by maybe 2 or 3 items. That's our expectation. So that's the first insight into the heat map. I would propose that if you are correlating more than 3 or 4 variables, this heat map output is quite nice to see, as you can recognize some patterns behind your data. So that's the first step before we start to export data by factor analysis. So that's the first step. So I would close this dialogue. And I would go back into my presentation. First of all, I would mention some assumptions for classical exploratory factor analysis. So if I would be perfectly correct, I should have the set of continuous or cardinal variables. Once again, I would like to repeat that we are usually differentiating nominal, ordinal, and cardinal variables. And if I have set of cardinal variables, so it means my observed variables are cardinal, factor analysis is prepared for these variables. Once again, there are some alternatives for shorter scales, unfortunately not available in JESP and other packages, but still we can also apply this small mistake included, these procedures for shorter scales, such as 4 points or 5 points we are using here. And my expectation is that there is some hidden dimension behind my data. So if I expect that my variables are not related at all, I wouldn't apply exploratory factor analysis. That's the law. If I'm not sure, I would perform as the first step correlations, such as this table or this heat map. And if I can see some patterns, so it means, for example, some items are closely related, I would perform factor analysis. So that's the first step. And let's go to the next step. I can also somehow evaluate statistically by test and criteria whether there is some relationship that is important, significant, and that's why it would be good to apply exploratory factor analysis. There are two well-known procedures for this task. There is a formal test, which is called the Bartlett test, according to statistician Bartlett, who invented this procedure. And there is also criteria which is called KMO, or sometimes it is also called in the literature on statistical packages as MSA. KMO stands for three names: Kaiser, Mayer, Olkin, who invented this criteria, and MSA stands for measuring of sampling adequacy. Doesn't matter which name we will use, but simple recommendation is that if this KMO or MSA is above 0.5, so maybe there is a space for factor analysis. For Bartlett's test, as it is formal test, statistical significant result, it means p-value below 0.05 is the sign for the usage of exploratory factor analysis. So first step for my data is that I would perform computations of these Bartlett's test or KMOs, and we would decide whether to apply factor analysis or not. We have at least some idea that maybe factor analysis could be useful, as at least 5 items are quite closely related according to this output, which is called heat map once again. So I would go into factor analysis and into exploratory factor analysis option. So first of all, there are quite a lot of options here. If you compare this dialog to the dialog in SPSS, they are quite different. So only I would like to warn you that if you are familiar with the dialog of exploratory factor analysis in SPSS, you wouldn't find many things here, and opposite is also true. And if I would like to find output which would tell me whether variables are closely related or not, I must go down up to the output options, and I must ask here for KMO test and Bartlett test. Once again, KMO is not technically test, but criteria, but take it as it is. Next settings I would like to ask is please use rotation orthogonal and select none, so we wouldn't perform at the first step any computation of rotations. It would be only time consuming, and I guess that nothing more is necessary to define here. So I would only take variables A47A up to A47K and move it into variables. Once again, as you can see, here is the picture of the scale or cardinal variable. So nothing else could be entered here. So no nominal or ordinal variables. That's why we changed the scaling of these variables into scale option. So if I move all these variables, I can wait a minute and JESP should compute for me KMO test and Bartlett's test of sphericity. Unfortunately, and this is one difference of JESP and SPSS, this KMO statistic is somehow merged into one table. So there is something that is called overall MSA and then individual MSA for KMOs. And here we have Bartlett test. So let's go back to these procedures. Once again, the main goal is to recognize whether there is some relationship for my set of variables and whether factor analysis would be useful or not. So I would start with the second table, which is called Bartlett's test. This Bartlett test is based on chi-square criteria. That's why there is chi-square evaluated here. And based on degrees of freedom, these degrees of freedom are related to the number of variables and also to the, let's call it, picture of my data. I wouldn't go into details. And here is the evaluation. Null hypothesis for this Bartlett test say that there is no relationship for these variables. It means A47A up to A47K. An alternative hypothesis says there is some relationship. It means factor analysis could be useful to discover some hidden latent dimensions behind my data. And as p-value is here 0.000, I don't know why here for this output there is no precise p-value such as here, but only this imprecise rounded to 3 decimal places is present here, but maybe that JESP producers will change it in a next version. But still, this p-value is very, very low. So I can reject null hypothesis and I can say, okay, it seems that maybe factor analysis could be useful for my data and maybe I would be able to discover some hidden dimensions. One warning, technical warning related to this Bartlett test. As it is statistical test, it is sensitive to sample size. So it means that if my sample size is bigger and bigger, going into 1,000, 10,000 and more, this Bartlett test would be statistically significant also for variables that are not closely related. So my recommendation is don't believe to this Bartlett test if your sample size is at least in thousands. And if you go back into my data matrix, I guess that my data matrix include nearly 2,000 cases. So I would be very, very careful about the interpretation of this result. The second criteria by which I can recognize and then decide whether to use or not factor analysis is KMO statistic, here called as overall MSA. So it measures relationship for the set of variables. Once again, recommendation is if KMO is above 0.5, feel free to use factor analysis. Here we have 0.816, and it's very good value, so we would perform exploratory factor analysis. And this output goes further, and it evaluates also the importance of individual variables, so it means A47A up to A47K in my solution. So not only I can evaluate the overall relationship for all variables together, but I can also evaluate relationship of this variable to the set of the rest. So I would go to individual values of these MSAs, and if some of these values would be low, once again, rough rule would be below 0.05, I would decide to omit this variable from my solution. And can you see some value below 0.5 or not? Is there some space for omitting of some variable?
No.
Okay, so in this first step, there is no space for decision, I would omit one of these variables. So I will keep all these variables for the next solution. So this is the first insight. So we have covered, I hope so, theoretically and also a little bit practically, introduction to exploratory factor analysis. And the last comment I would only add, and then we would make the first break, is a brief description about the difference of exploratory and confirmatory factor model. And I would also briefly cover the topic of difference between principal component analysis and exploratory factor analysis. So only for you to know about these differences. So here we have slide number 9, and pictures here are trying to differentiate between exploratory, it is left panel, and confirmatory, right panel, factor analysis. So my question is whether you can see some difference and what is this difference about? So I will try to describe these differences. So first of all, as you can see on this left picture, exploratory factor analysis, I do not have any idea what are the factors behind, and I would like to compute all these relationships, all these lambdas, and according to the values of these lambdas, then maybe I would interpret the factor 1 as something what is common for first 2 items, and factor 2 as something what is common for the second 2 items. So I am exploring my data and I am trying to imagine what is behind my items. That's the main goal of exploratory factor analysis. For confirmatory factor analysis, the logic is quite different. So I have quite strong expectation, maybe strong hypothesis that there are 2 factors. First factor is created by 2 items, the second one by the rest. And I have also maybe expectation that these 2 factors are related. And I would like to confirm, that's why it is confirmatory, I would like to confirm that my hypothesis or my expectation is correct. So it means here I would be performing some formal statistical tests, and we would learn more about this confirmatory factor analysis in 3 weeks, I expect. So that's exploratory version and confirmatory version. And I would go down to slide number 15, also to differentiate between principal component analysis and exploratory factor analysis. So here we have exploratory factor analysis, the picture which is quite familiar for us. So here we have some hidden dimensions. In JESP, these are called PCS, principal components, but this is, according to my opinion, mistypo in JESP. And here we have one-headed arrows going from factors, hidden dimensions, to our observed variables. And here we have only arrows which are standing for random arrows here. And here we have the picture of principal component analysis. And I would like to ask you if somebody can help me to say what is the difference between this picture of exploratory factor analysis and this picture of principal component analysis. What is different logic behind these 2 pictures?
In the first picture, arrows are directed towards the principal components.
Yeah,
from
here
variables.
we go from manifest to latent, and here it is just opposite. Yeah, okay. And now I would like only to add some comments. So for most of phenomenons, this exploratory factor analysis is maybe much better. For example, here's the intelligence, here are results of the test. Here is, for example, left-right scales, and here are items measuring left-right scales. So it means our expectation is that here we have some concept, something in my head, And here I have some observed manifestation of these concepts in tests or in questionnaires. But maybe sometimes also in sociology, there are cases for which this idea of principal components, so it means here we have some indicators and we are creating some common principles behind can be more useful. Do you have some example of such case for which maybe principal components logic is better than EFA? There is at least very well-known sociological concept that would follow this pattern in spite of this. Instead of this, excuse me. So some idea? So I would say that the logic of social status, or maybe individual capital such as cultural capital, social capital, human capital, financial capital, or economic capital would follow this logic, as they do not exist in reality. These are only concepts which were created by sociologists. But I have individual items measuring, for example, economic capital, for example, income, those of etc., etc. And by these variables, I am somehow computing capital which is behind, or social status. So you should only know that there are some cases for which this principal component model is better than EFA, or maybe is logical. Technically, in statistics, these models are very, very close to each other, and also the results are very close to each other. You will see after the break, we would perform principal component analysis as well as EFA for the same data, that also substantive results are very close to each other. You have here pictures which are closely related. Only this picture expect there is some relationship between components, here not, but we could change it. So technically, we can exchange principal components and EFA, and that's why also these two are somehow mixed in some statistical packages. For example, in SPSS, you would find principal components as the part of EFA dialog. So this is only last information related to EFA and the discussion about principal component analysis as very close technique. Only if we would like to find equations behind, of course, the logic would be reversed. So it means this would be dependent variable, these would be independent variables, and all the same would be nearly the same as for EFA. So I would stop sharing here, stop recording.